Okay, so here what we have is the image segmentation, which refers to another step in image processing or the methods where inputs are the images. Just a minute. Is it visible, everybody? The presentation is visible, no?
Yes, sir.
Okay. So the segmentation refers to another step in your image processing method where inputs are images and an output are attributes which are accepted from the images. Okay. It is the subdivides which an image into the constituent institutions or the objects. Now segmentation, the accuracy determines the eventual success or the failure of your computerized image processing. Okay. This is what the meaning of your, we can say, image segmentation. For example, your autonomous target acquisition, that is also one of the application of your image segmentation. Segmentation algorithms are based on the one or two basic properties of intensity values, that is discontinuity and similarity. So let's see what exactly mean by the discontinuity. Okay. Now you can see here the segmentation algorithm are based on the one of the two properties of discontinuity and similarity. Discontinuity, an approach it is into the partition of an image based on the abrupt changes into the edges. Okay. Similarity, the approach is to partition the image into image based on the similar regions according to predefined criteria. Okay. So such as threshold engagement, then region growing, region splitting, and merging. This is what all the examples of your segmentation. Now, there are three, what we have the image features which we are going to consider for the segmentation. One is called as the point, second one is called as the line, third one is called as the edge. So we have three features on the basis of which we are going to go for the segmentation. Now, the edges. Now, edge pixel, the pixel at which the intensity of image changes abruptly. That is what your edge. Now, edge segments are the set of connected edge pixels. Okay, so local averaging will smoothen an image. Okay, and averaging is analogous to the integration in terms of we can say the pixels. The local changes into the intensities can be detected using derivatives. The first and second order derivatives are the suitable one. Now, the derivatives of a digital function are defined in terms of differences. An approximation which is used for first derivative, it must be zero in the areas of consistency, then must be non-zero at one set of intensity, step or ramp. It must be non-zero at the point along an intensity ramp. An approximation used for second derivative must be zero in the areas of consistency. The same will be applicable to approximation using the second derivative. Okay, then this is how your point or line of edge detection will be there. Okay, now considering the properties of your first and the second derivative as we traverse from the left to right, initially we note the first order derivative is non-zero at onset and along the entire intensity ramp, while the second order derivative is a non-zero only at the one set and end of the ramp. Okay, now the first order derivative produces the peak edges, second order derivative produces the stronger responses to the finer details. For example, thin lines, isolated point, and the noises. Okay. Second order derivatives produces a double-edged responses at the ramp and the step transition in intensity. The sign of second order derivative can be used to determine whether the transition is into the edge is from light to dark or dark to light. That is what the sign of your second order derivative. Now, the special filter which can be fulfilling the requirement of your first and second order derivatives are used in case of your we can say the edge detection. Then we have the point detection. Now using the Laplace mask, we can say The point at the location x and y is detected if absolute value of the response of a mask at the point is exceeds the threshold value. Means a certain value has been fixed, and to that point, through that value, we have this point which has been located, whose amplitude has been checked, and according to comparison, what we are getting the point to be detected. So such points are labeled as 1 in an output image and in others 0. So thus producing a binary image. So g of xy is equals to 1 if r of xy is greater than or equals to t, where t will be the threshold. Otherwise it will be 0, is it? So that is what mentioned over here. Ideally, the intensity of an isolated point will differ from surrounding, thus it is easily detected. Okay, now next what we have with us, the line detection. Now here we can expect second order derivative stronger responses and produce the thinner lines than the first derivative. Thus, we use the same Laplacian mask for line detection as well, but the mask is isotropic, so its response is independent of direction. Okay, independent of direction as well. But the mask is isotropic, so its response is independent of direction. With respect to 4 dimensions, that is 3 by 3 Laplacian mask, vertical, horizontal, and 2 diagonals. So we may need to determine the line in a specific direction. So now you can see here the masks -1, -1, -1, 2, 2, 2, 2. This is what the horizontal. This is what how the plus 45 degree. This is how the vertical alignment of your point direction, and this is what the minus 45 degree alignment. In this way, your point detection mask will be applied horizontal, vertical. Then the let R1, R2, R3, and R4 denotes the responses of the mask from the horizontal plus 45 vertical to minus 45. And if at a given point in the range Rk is greater than Rj, where j is not equal to k, jth column is not equal to kth row, then the point is said to be more likely associated with the line in the direction of your mask k. Okay, we can say that. Now, the age models. Now, third point is age models. What do you mean by these ages? It is an approach which is used most frequently for segmenting the images based on the changes in the intensities. So age models are classified according to their intensity profiles. So we have the step ages, then we have the RAM ages. Where step ages involves step ages, it involves the transition between two intensity levels occurring ideally over the distance of 1 pixel. So it's a computer generated image. Okay, then we have the ramp age, that is digital image with the age blurred with the noise with a degree of blurring determined by limiting its focusing mechanism. The slope of ramp is inversely proportional to the degree of green. Now what we have the next is the root of age. Now root of age are the model of the line through a region with the base of a roof age being determined by the thickness and the sharpness of the line. For example, in the range imaging, then when the thin objects are closer to the sensor, pipe appear brighter. Digitization of lines drawn in the satellite imaging road rocks, which looks like shown in the image. Okay, so age linking and the boundary detection. Ideally, the age detection should yield the set of pixels only onto the edges. Actually, these pixels seldom the characterized edges completely because of the noise. Then break into the edges due to non-uniform illumination and other effect that introduce the superior discontinuity in the image. Yeah. So age detection is followed by age linking algorithm. This is how the age linking will be there. So the local process. So one of the simple approach of age linking is to analyze the characteristics of the pixels in small neighborhood about every point x of y that has been declared as an endpoint. So the two principal properties used for establishing the similarity of your age pixels in this kind of analysis are the strength, the direction of your gradient vector. So these are all the two principles which are used for establishing the similarity in between the ages of the pixel. In this kind of analysis, we have the strength and the direction of the gradient. So let S of xy denotes the set of coordinates of a neighborhood centered at a point of x of y in an image, and age pixel with the coordinate s of t. In S of xy, is similar in the magnitude of the pixel at xy if m of s of t minus m of xy magnitude is less than or equals to e, where e is a positive threshold. That is what the meaning. Then the direction angle of a gradient vector is given below. And age with the coordinates s of t in s of xy has an angle similar to the pixels at x of y if your magnitude of f s of t minus alpha of x of y is less than a, where a is a positive angle threshold. A pixel with the coordinate s of t and s of xy is linked to the pixel at xy if both the magnitude and direction criteria are satisfied. Now, the global processing using your Hart transform. Now, here we have developed an approach based on whether the set of pixels lies on the curves of the specified shape. Once detected, these curves from the edges of the region boundaries of interest. Given the endpoints in an image, suppose that we want to find the subset of those points that are lies on a straight line. So one solution is to find all the lines determined by every pair of points. Then we need to find all the subsets of points that are close to the particular line. So this approach involves finding. This approach involves, we can see, finding the n into n minus 1 divided by 2, which is nearly equals to n of 2 lines, and then performing the n into n minus 1 divided by 2, which is equals to n3 comparison of every point to all the lines. Okay, so now what actually mean by thresholding? Suppose an image f of xy is composed of the line objects on a dark background. The following figure is the histogram of the image. Now you can see this is what the image with the dark background, light objects. Okay, then the objects can be extracted by comparing the pixel values with the threshold t. Okay, then once the way to extract the object from the background is to select the threshold t, and that separates the object from the background. At any point x of y for which f of xy is greater than t, it's called as an object point. Otherwise, the point is called as the background point. Then g of xy is equals to 1 if it is f of xy is greater than t, and g of xy is 0 where f of xy is less than or equals to t, where t is the constant which is applicable over the entire image, and then the above process is called as the global thresholding. Okay, so this is what we are calling it as a global thresholding. So this thresholding is required in case of what? The point and the edge detection. Now we have seen the edge and the line detection and the point detection, where this threshold is used to compare with the amplitude of the pixels, where we are actually modifying something or we are enhancing something. Okay, so here we can see when the value of t changes over the image, then the process is redefined or referred as variable thresholding. Then sometimes it is also termed as the local or regional thresholding, where the value of t at any point of x of y, okay, x of y in an image depends on the properties of neighborhood of x of y. If t depends on the spatial coordinate x of y themselves, then the variable thresholding is often referred to as dynamic or adaptive thresholding. Okay, then we have the multi-level thresholding. It is also possible to extract the object that have a specific intensity range using multiple thresholds. Okay, so here we have the image with a dark background with two light objects. Okay, so the extension to the color images is straightforward. There are three color channels in each. One specifies the intensity range of the object. Even if objects are not separated in the single channel, they might be with all the channels, and applications are, for example, detecting, tracking the face based on the skin color. That is what the multi-level thresholding. A point x of y belongs to the object if a t1 is less than f of xy less than t2. The another object class if f of xy is greater than t2. The background if f of xy is less than or equals to. Okay. G of xy is equal to a if it is f of xy greater than t2. G of xy is equals to b if t1 lies in between f of xy and t2. Then g of xy is equal to c if f of xy is less than t1. Now, the region-based segmentation. Now, region growing. The region growing is a procedure that grows pixels or a sub-region into the larger regions. The simplest of these approaches is pixel aggregation, which starts from the set of zero points from these which cross the region by appending to each seed point those neighboring pixels that have similar properties such as gray level, texture, color, and the shape. So the region going based on the techniques are better than the age-based techniques in noise image, where the ages are difficult to fix. Now, the region splitting. Now, how that image got split into these small regions. Now you can see R1, R2, R3. Then this R4 has been divided again into R41, R42, R43, and R44. Okay, so this region growing starts from a set of seed points, and alternatively it starts with the whole image as in a single region and subdivided into regions that don't satisfy the condition of homogeneity. The region merging. The region merging is opposite of region splitting, which starts with the small regions 2 cross 2, 4 cross 4 regions, and merge the region that have similar characteristics such as gray level and the variance. Typically, splitting and the merging approaches are used iteratively. Okay, so this is what your region-based segmentation, thresholding, which is applied to the images. This is how the detection is going to be done in case of images, the point, line, and the edge detection. So we need to think on this. Okay, and these are the features which are used in case of image segmentation. Now we have seen the concepts of closing, opening, then thinning. Okay, this hit and miss transform. These are all the things we have already covered in the last lecture. What is erosion? What is dilation? Or how the segmentation is going to take place, or how the erosion is going to take place. Okay, basic concept of your set theory. What do you mean by this morphology and this segmentation? That is what we have seen in the last lecture. Okay, so hope everybody have got this. Is there any doubt in this now? Up till now? Any doubt in this? Yes. Any doubt is there? Yes. Whether I'm audible to everyone?
Yes, sir. No doubt.
Okay. So this is how the region and the region-based segmentation, where we have the region growing and region splitting and region merge. So region growing is the procedure where the group of pixel or sub-regions are into the larger regions. Okay. This is what we have learned in the image segmentation and morphological operations. Okay. So these were the points for your today's lecture now. Okay. Here we I think completed the fourth one as well. Let me check the syllabus. Just a minute. Then we will proceed. Just a minute. I hope my screen is visible to you. Now you can see this is what your unit number 4, image restoration we were talking about, or image segmentation and morphological operation. Okay, unit 3rd, sorry, not unit 4. I think we have completed this as well. We have started with the degradation model, noise model, and that also we have covered. First, we will be concentrating on this. Today, we have completed this unit number 3. Okay. So here you can see point line edge detection, edge linking with hub transform, then this region-based segmentation, dilation, erosion, opening, closing, hit and miss transform, thinning, thickening, and the boundary extraction of your images. That part we have completed into the segmentation and morphological. And in the next lecture onwards, we will be starting with the image restoration. I think in the image restoration also as well, we have seen this degradation model, noise model, estimation of your degradation function by the modeling as well. This last point is remaining from this chapter as well. Okay, so I have repeated this today, this image segmentation and morphological, as huge gap was there during the lectures. So I have repeated this point today. Okay, so hope everybody knows about this image restoration. We have talked about it. What is exactly the restoration and image enhancement? The difference we have seen. Then we started with this degradation model and this noise model as well. Huh? Okay, so hope everybody will get it. Hmm? The last point, that is manual filter and the inverse filter were remaining in case of the fourth chapter. Once we have completed this fourth one, we will be starting with the fifth chapter, that is video formation and perception and the representation. In that we are going to see these 3 points: digital video sampling, video capture and display, sampling of your video signal, and at last we have the two-dimensional motion estimation, where the optical flow and the methods will be there. So this is how your fifth and sixth chapter will be there. So we will be taking the revision of third and fourth again, so that you will be in touch with that. So these were the points for your today's lecture. Hope everybody have understood that. So if anything you want from my side, you can just tell me. Otherwise, you can just put your roll number into the chat box and you can leave the session. Okay. You can just put your attendance into the chat box and you can leave the session. No issue with that. Thank you very much. Someone's mic is mute, I think unmuted. Please mute yourself.